So we're ready for 9B part 2. So set up your page, 9B, and this will be part 2. And remember that 9B is really pretty simple and straightforward. It says describe the postulates of the kinetic molecular theory. Okay, so yesterday, or whenever you're taking these notes, for the first part of 9B, what we did is we stated here are the 5 postulates of the kinetic molecular theory. Gases are made of really small particles. The volume of each particle is nothing when compared to the distance between the particles, so we can ignore the volume. The particles are in constant random motion and are colliding with each other and with the walls of the container, and that's pressure. And remember, in our atmosphere and whatever you're in, you are considered part of the container, so you feel that pressure on you. 4, the gas particles don't attract or repel each other, so there are no IMFs, and that means there are perfectly elastic collisions between them, so they don't lose energy when they hit each other. And then 5, the average kinetic energy is proportional to the Kelvin temperature, so we have to use the Kelvin temperature scale when we do this. The next thing that we deal with here is just in general, what are ideal gases? Ideal gases are gases that obey all 5 rules or all 5 postulates of the kinetic molecular theory. And because they obey those, then it's easier for us to do our calculations here. Gases are most ideal. Okay, so we know that nothing's going to be perfectly ideal. I mean, that's just reality. And so we talk about ideal gases, and then we'll talk about real gases. When we talk about ideal gases, gases are most ideal when they are at low pressure and high temperature. If they're at low pressure, it means they're spread out. When it's at low pressure, all the molecules, the particles spread out. They can spread out all the way throughout their container. And when they're at high temperature, they're moving really fast. So you have 2 pieces here that make it do that. So at low pressure, the particles are very spread out. Remember, a gas will take up its container. That's one of the things about gases that we talk about compared to solids and liquids. Gases have, they take the shape of their container, they spread out to fill up that container here. So the particles are very spread out. And the volume of the individual molecules, again, can be ignored. Okay, and at high temperature, then the molecules are moving so fast that the IMFs have no effect. So if there are any IMFs, like water being polar, for example, it doesn't matter. And again, we can ignore them. Now, that's ideal gases. If we take into account, if we say, oh wait, but what if it's at high pressure, so the molecules are really close together, and low temperature? And an example of this would be right before a gas is changing back down to a liquid. You have increased the pressure or you've decreased the temperature, you've decreased the temperature so much that it's about ready to condense from a gas back down into a liquid. So now what we talk about is we talk about real gases. Real gases are when you've got them at low temperature and high pressure. So you've squeezed them back together. They're close to changing back to a liquid. So that gas is close to changing back to a liquid. And if you have this situation, you've squeezed everything so closely together, you've slowed everything down so much that now you have to take into account the individual molecules, the volume of the molecules and stuff, and the IMFs. And when you look at the equation for these, it's hideous, it's ugly, you don't want to even see that. But you can Google ideal real gas law equation or something along those lines, and it'll pop up and you'll be able to see that. Okay, so when we deal with gases, this 9b, they have to follow that kinetic molecular theory, the postulates of that. Okay, so the difference between ideal gases and real gases. Ideal gases, high temperature, low pressure. Real gases are right before that gas is changing back into a liquid. That's the easiest way to think about what it is. Now there's one more piece of information that we're going to talk about before we get into all the gas laws. That's STP. You're going to hear this STP a lot. And STP is not, I'm not talking about that stuff you put in your car. STP stands for standard temperature and pressure. And standard temperature and pressure is 1 atmosphere of pressure, 1 atmosphere of pressure, and 0 degrees Celsius. Notice they use Celsius in here, even though we're going to change everything to Kelvin. So if that were 0 degrees Celsius, it would be 273 Kelvin. These two, this piece of information right here is really useful. It's really important. 1 atmosphere and 0 degrees Celsius. If you look on WeatherBug or some other weather app and you look for the barometric pressure, usually they're going to give it to you in millimeters of mercury or inches of mercury. And if we use these in the lab later on, you can just Google change inches of mercury to atmospheres, and it'll pop up on your screen for you. But I usually, in almost all of our equations, I'll use atmospheres. However, you're going to find that pressure can be measured in a lot of different units of measurement. Pressure, you're not gonna like the units of measurement. So it can be measured in 1 atmosphere. Right now at sea level, 1 atmosphere is typically what it is. At 0 degrees, it'd be 1 atmosphere. Or it can do it in 760 millimeters of mercury. Okay, this thing right here is a unit of measurement. This thing right here is a unit of measurement. You can measure it in kilopascals. And if you look on your yellow pages, find the section that talks about gases. I think it's page 5. Look at these things. Millimeters of mercury, a torr, and that's just named after a scientist. So 760 torr is the exact same as 760 millimeters of mercury. It can be measured in pascals, in kilopascals, and then in pounds per square inch. All of these are equal to 1 atmosphere. And so I usually use 1 atmosphere because, 1 atmosphere, when you are multiplying or dividing by 1, it just makes life much easier if it's at 1 atmosphere. So you're going to need your yellow pages to deal with this stuff. Hello?
Hey, Miss Howard, this is Mr. Gentry.
Yes.
And I need to find out, do you have some packets made up that I was supposed to take down to the cafeteria?
They are all on my back lab table. They're all in my room. All of the science people put all of their stuff. I think most of them are back there.
Okay, so they're in your room?
They're on the back lab table and they're all labeled.
Okay, let me, I'm going to head that way. Hold on.
Okay.
I'm going to double check, make sure, because I didn't see anything. So
Unless someone took them down there. Medlin said she was going to take them down.
Who did?
Medlin, is she there yet?
That I haven't seen.
Okay.
Mr. Cameron told me to check something, and then she told me to go ask me. But I'm going to go over here real quick. card.
Okay.
Walking the hall here. You hear the house past that thing with a voice vote to keep all those people getting money that
Oh, yeah.
had to leave their jobs.
Yeah.
So that was finally a good thing.
Yeah, finally. Finally.
Well, it took forever with the Senate. You know?
I know. Yeah.
The Democrats that were doing
Exactly, yeah.
ridiculous stuff
Yeah.
on there that was okay. Should be back here.
Yeah, it's
In
all
the corner by the lab, where the lab shirts are.
that should be, if you open my door, it's all lined up. There's a box of stuff and it's all got orange post-it notes labeled what everything is. Is it back? Do you see that?
Okay, it must be gone. It's not by the sink.
No, it's you. Yeah, you walk in the door and it should be lined up all along that first lab table. If it's not, it should be obvious.
Okay, all right. Yeah,
Okay,
all
so
right.
then somebody took it all down. Okay,
All right. Thanks a lot.
okay, bye-bye. Okay, sorry about that. So when you deal with pressure, there are going to be some really ugly units of measurement. So you have got to make sure that you can tell what's a unit of measurement and what is just a variable like X.